Hey everybody, this is Brad Duck talking to you in regards to some conceptual stuff. I do hardware videos and I also try to do something mental, something associated to the world of technology and science. So there were two things I was going to bring to the table. The first one is called, can you do more with your home lab environment? I've had this series of this going on for a while, and the answer is yeah. There are some new ideas out there that you could tinker with using Raspberry Pis and your servers and a little bit of database work and so on. I'll talk to that secondly, but the first thing I'm going to talk about today is something that seems to be like kind of new, but in truth isn't new. Now, what I'm referring to is optical computing. What is that? Well, remember in Star Trek and Next Generation, they used to pull out these little chips that were kind of clear through, kind of translucent in some places. Well, those were called isolinear chipsets. And basically, they worked on a photonic level. Now, working on a photonic level means that you're using photons instead of electrons to correlate your data collections, transactions, executions, transistor reactions, and so on. And with that being said, there's some really super benefit of running with photonic-based technologies opposed to electronic technologies, which literally would be saying going from the proverbial riding in carts in 13th century to flying in an airplane. It's that disparity. So with that being said, let's talk about it. Now, unfortunately, I know you might be seeing some noise out there about Intel's introduction of basically integrating photonic-style CPU computing and GPU computing, which is not new, but has a new spin. About 15 years ago, roughly, I believe, memory serves me correct, there was a lot of experimentation with what we call the optical motherboard. And what that was is we didn't have the technology to take the CPU at the CPU level and integrate technologies of photonic strategies, but we could make the bus. That's the roadmap of the unit, right? And it's the motherboard, if you want to call it, in this case. And inside it, it has optical pathways opposed to copper pathways. So as you've seen with motherboards, let me give you an example. Motherboards have what we call copper pathways, which are in multiple layers through the thickness of the motherboard itself, right here, and that they're present on both sides. Now, normally the die cast, in this case, this board is built with the soldering functionality mostly on one side, and then, of course, the logic being put on the other side. In some versions, they have it on both sides. Just depends on the technology and so on. But this Asus motherboard, in this particular case, this is a Z390P, the Asus Z390P, uses pure copper for the bus of the motherboard that the CPU communicates on, and goes back and forth with. Now that is where we are today, but like I said, there were some prototypes made about 15 years ago that actually had light up pathways. They were pathways that would actually allow you to do quite a bit. And because they were using fiber optic relay points, they still had the problem of transferring, once it got to its source destination, back into an electrical current so it could ride on copper and go on. So the idea logically made sense, but the results weren't very promising, because if you have to go from copper to fiber back to copper, where's your benefit? You kind of lose it between the translation processes. And so it didn't take. And I saw 3 of these motherboards, and they were pretty unruly. They were pretty bulky. What we call the full AT style size logic boards. They were pretty big. But it was really neat to see that inside these small laser-driven optical relay points inside the motherboard would act as the bus. It was an action and an experiment, that's for sure. But the real way to make this work is to get optical integration into the actual die of the CPU. So when you look at the CPU die itself, you know that as you observe it, there's overlays in it that allow you to use optical relaying. And they see the key thing about optical relaying from point A to point Z is the frequencies. So what that basically means, unlike electricity or electrons, light travels in many ways. And there's much inside that pathway of light, and we call those frequencies. So you can actually have dozens, hundreds of frequencies running on different wavelengths inside that pathway, providing you a data bus that's staggering. Now, that in equivalency in itself is impressive and kind of starts to touch in the direction of the biological nature of our own human brains. Now, for that to be fully functional and capable, the nature of quantum technology has to come way down from where it is today, and their high pedestals, as I like to call them, as they're trying to establish the nature of how quantum computing can exist both in a linear true quantum state and also in a CPU simulation state, which, by the way, if you've got at least 12 core processors, that could give you basically 3 atoms, or 3 processors, one representing 0, one representing 1, and one representing 0, 1, to simulate the nature of quantum technology. It's slower, but it can run the code and it can do everything you would expect as you would see from a sample testbed. But nobody's done that yet, nobody's built that yet. Might be an idea for somebody to do so. Now, with that being said, one of the key thing about linear natures, unlike parallel natures, where we have the ability to, let's say, see and receive, or write and read at the same time, which is natural in parallel states, the challenges with fiber optic nature is that it's mostly one direction. I've not seen any introduction of technologies that can allow what we would call segmented frequencing, where a lower batch of frequencies are down here and they're being sent and the other side is receiving those, but then it has a transmitter of its own that's emitting on a higher block of frequencies on the same fiber. That would make these pretty big and pretty bulky, but that would be the only way you could do that. So most of the time, most likely, it would follow the same strategy as SMP motherboards, symmetric multiprocessing, where that one fiber optic pathway is just that. It's a pathway in one direction. I haven't seen the documentation follow-ups on that just yet, but you could either go one way or you could go the other way, but you can't go both. So the key thing about that is it adds a value to the nature of what we call one-way directional data. It can't be corrupted, technically speaking, from the sender to receiver, unless you physically damage the board. That's really great. That means no CRC related impact errors or corrective states of electron errors. There are a lot of problems, believe it or not, that we've accomplished over many decades to streamline electronics to a place where it is able to incur errors, natural errors caused by the environment, caused by the nature of metal, and so on, that they can self-correct. With the optical environment, photons don't work quite the same way. They don't have the impedance of matter. The only thing you can do is break the path. That's it. And pretty much outside of that, it's one of the biggest reasons why we migrated to a fiber optic environment, because we could get away from all of the all the copper-related issues you'd have electrically wise with copper wire. But cost is cost versus efficiency. So today we still use Cat 5, Cat 6, and so on, because it's just cheaper. You know, they haven't figured it out yet to make fiber the standard. To do that, you have to produce it and make it available in a more cost-effective manner. But you know markets, they are a different beast. Now, the second part of my presentation here today is about what can you do outside the box versus what you've done today with your IT server lab. May it be a mini lab, like a Raspberry Pi environment, and so on, or a hybrid. We're using cloud services and servers and Raspberry Pis, or you have high-end systems like I've got, and these allow you to be able to do quite a bit, actually, in regards to accomplishing all the basic, today kind of stuff. But here's an idea. There's this little sensor, and it's roughly about the size of this right here. Let me grab this. It's called a Hall's effect sensor. It's really small. Kind of looks like a LED or a resistor. And the Hall effect sensor has one very important function. It detects magnetic fields. Now, they have basic sensors and they have some more, what we call more encompassing sensors that can pick up natural magnetic fields as well as electrical magnetic fields. Very important. But what if you could, with your PC lab, experiment with the nature of creating what's called a 3 retrospect Hall effect magnetic locator sensor? It's really cool. Now, I'll explain later why you might want to consider this idea. If you're like me, or you're like others who are in the IT industry, it's important to know about the weather, right? It's also important to understand the nature of your environment. And we tend to be super cautious about our equipment, and magnetic fields, polarizing magnetic fields caused by static discharges, are important. So, this is why I bring this up. Now, you can also use this, if you build this the right way, to scope long distances and monitor magnetic fields from a great distance. You can also build this with a couple of additional items that can allow you to see ultraviolet or infrared spectrums too, which work together with the magnetic field information to tell you what's going on. So, what does that mean? Well, what it basically means is if you take a single Hall effect sensor and you get a magnet near it and you take it away, it's going to build up a charge and it's going to let go of a charge. And that resistance effect causes the Hall effect to send a signal through the analog 2-wire connection to an analog board, which then would say, hey, something's getting close to me. And here's an example. Here's an example right here. Now the Hall effect, in this case, is inside this little guy. And when you turn it on, and you get it in place, and you set the sensitivity value and the ultrafine value, the inside here is the single Hall effect sensor with an LED on it. And when it gets close to the magnetic field or away from it, it can tell you, and mathematically too, by the way, if you use a little bit of math on the information, roughly the distance of where this object is and where is it coming to or from. The coolest thing about that is that we've always done it this way, because if something got close, this light would light up and go, then it would shrink down. And it's based on the resistance of the Hall effect sensor. Now, we're not in the 70s. How would you make this better? Here you go. If you create 3 pathways, in other words, 3 sets of Hall effect sensors, and you parallel them, in other words, you put them in tandem, in a straight parallel line, right? They're all connected, but they're longer. And because they're longer and there's more of them, they're more sensitive. You can also individually wire them to get proximity effect, which is a different approach. Now, there is documentation on Hall effects. That's not what I'm getting at here. Creating the sensor stacks are pretty easy. It's just a small circuit board, some soldering iron, boom, you're done. Then you would use an analog to digital conversion board. And I would suggest you use an analog to Wi-Fi. And what that would do is it would send that information to its source node, and it would receive the information by wireless Wi-Fi, and you're seeing the telemetry that's coming from the Hall effect tower stack of sensors. Now, if you had 2, then you can actually begin to get ranging. Now, if you've ever seen the 2 antenna structure, they can monitor a magnetic object and watch its angle and exit and get reference and speed and things like that. You also see this in some of the shooting environments. They have the same kind of setup. But if you had 3 of these stacks of Hall effect sensors, and this takes a little bit of math, and now you're starting to be an IT guy or gal. You're getting information from 3 separate stacks from 3 different locations that allow you to do something incredible. It allows you to triangulate the exact location of where the magnetic field is. It doesn't take a lot of sensors to give a lot of sensitivity. And if you've ever noticed on an airplane on the front, if they ever take the cone off, you see this subcone, and it's got these lines that you see. And what they do is they take those are 3 separate lines of sensors that, with some mathematical equations in some software code, and in our case, what you do is you put it into a database and compile the information that way, you would be able to actually monitor where something's moving about. Now, at the beginning, you won't be able to do it in real time. Eventually, you can by using some advanced logic and a little bit of AI integration. But think about it, guys. You can build yourself a sensor effect that can tell you when your building's at risk. And it can tell you that, okay, I need to make sure my UPSs are in good shape. And this is not something that just happens. It doesn't. A lot of times, magnetic fields, and based on how you build your sensor arrays, can tell you when, thunderstorms are going to get dangerous. Dangerous means lightning. Lightning means damage, right? And so that gives you the ability. Now, you can also supplement the sensors with visibility. In other words, an electromagnetic spectrum sensor. And what that does, it just basically gives you, it's the same effect, by the way. It's a sensor that has the EMS sensory functionality in it, but you have to stack them and build their sensitivity to make them more responsive to kind of pair up with what your Hall effect sensor array is going to look like. And then you've added infrared, or you've added ultraviolet. Now remember, people, these aren't cameras. These are sensors. They see a blip, and it's X amount of values away. And it requires 3 of these to be able to do triangulation effect. But the cool thing about it is the triangulation effect will confirm the magnetic field or not confirm it. And you can actually have anomalies in existence that are ultraviolet or infrared spectrum and have nothing to do with magnetic fields. And that's something of value too, because it allows you to be able to complete the picture that you have outside. Now, for all of you UFO enthusiasts out there and stuff like that, yeah, I guess, a weird kind of way, this is a way you can get around the United States, National Security Act to secure specific types of ultraviolet cameras that see in a specific spectrum, because they don't want you to see what's there. And it's disconcerting. And to me, that's such a thing. I can't even talk to it. But a sensor is not the same thing as a camera. It's not about putting something on screen. It's about confirming something is present. And ultraviolet spectrums, or EMS spectrum sensors, have been around for a long time. And, it's something you can play with. You can add other spectrums into that equation too. Now, you can't truly add an EMS spectrum device because that's too much. You have everything from gamma rays, X-rays, all the way down to sound waves. No, you just can't. I mean, that's not possible. You have to be very selective on the frequency levels that you're trying to work with. But most of the sensors in the spectrum of infrared, they're just that. It's just a small spectrum of the total spectrum, and that's not hard to do. Same way with ultraviolet. Same with X-ray. Well, not X-ray because that's expensive. But there are many different types of spectrums that are out there that you could cost effectively be able to build in, and you can build a very intelligent sensor platform that can sit on the roof, and it doesn't have to be big. It's no more than 2 or 3 feet wide, and you can mount all the sensors on it you want, run that analog output out to your converters, and just have them come in as nodes. They're dumping their data into your metadatabase system. You can also put motion sensor platforms in there that would add more security to your home, because it would tell you exactly where motion is happening out there by using what's called proximity motion detectors. And they work on a much grander scale than a simple house sensor. So that's something that's nice. And you can do quite a bit, especially in correlation with what's called a DOM style BUZI camera control system that can zoom, can move, pivot, and focus on that target, just to kind of give you some graphical representation or photography-based representation of what your sensors are seeing. It would be nice to be able to put a picture to it. Now, if you did that, here's my recommendation. Don't put a basic DOM camera, like a 1080 or a 760 camera, out. Don't do that. Those cameras, they're like this. These, they don't work. But the DOM is basically an enclosure that goes around the camera, and it's motorized, so it can go up and down, left and right. And you put what's called a 4K minimum or an 8K camera in that, and that's not cheap. But the reason is, here's why. You see, an 8K camera or a 4K camera does more than your eyes can see. It sees more than you can see. And it sees it, it's such a detail that the minute values we can't see, it does see. We call this erroneous data. And erroneous data basically, or erroneous style data input, is data that we collect in sensor stacks that are present but don't relate to what we're focusing on. But if you step back, if you stepped out of your sandbox and you looked at it, you can actually take all the unseen data and put that to input and then characterize it. In other words, give it a color. Like if you see this particular pattern, connect the dots. You can use an AI engine to construct the dots to see if they represent something. And what it does is it's showing you a lot more than what our eyeballs can see. But the only way that you can truly see them is first you identify the invisible by the data points it creates on your sensor stack and your camera stack. Then what you do is you collate them together to formulate what they look like, and then you give them a color, like blue lines, or all of this I see, I want it to be in red spots, or that way you can formulate the shape yourself, and so on and so on. So this is abstract vision, basically, is what I'm talking about. And again, it's still not a big device. It's big, about 3 feet wide. Your sensor stacks are there. Your little Wi-Fi modules are on the bottom. They send out the signal to home base, and it's just data input. It's not difficult. I'll tell you, all of the science industries really don't have a monopoly on this. And your home computer systems, your computer labs, especially if you've got databases, you can compile this stuff and really find out some really awesome stuff. And you can confirm it. Now, with that being said, there's so many more things I could talk about that you can do outside of a basic lab. And some of those relate to the health and the air in your home, and metafilament control, and just a whole lot of other things that can allow you to do things, including considering businesses, business services. But for today, I just wanted to talk about graphical computing, or in other words, an optical-based computing platform. And I wanted to talk about, a little bit of fun on the side with playing with Hall effects sensors. I have a diagram that I have my father made back in the 70s for me, and I used it several times to work with some inversion field generation work I did a long time ago. I still have that inverter up there, and it was fun to play with. It was with plasma, and it had a lot of discovery with it. I enjoyed it. I think you can play with this stuff and have some fun with it. And you can watch the weather come in, and you can see how it comes into your environment and watch how it affects your local environment, and give you warning, potentially. But for now, this is Brad Dyke saying God bless, and I hope you guys have a great weekend. You take care. Bye-bye.